Rivers are arteries of life. As visible on this impressive map, they are very important features of our landscapes. Like blood vessels, they allow for distribution of nutrients, organisms, as well as processes along their corridors. They connect ocean environment with terrestrial environment, and they are probably responsible for the way the life distributed from the ocean into the land. Therefore, they are biological distribution pathways which provide transportation, which offer communication, as well as the ways the processes are distributed along the river corridors, processes of chemical, biological, and physical nature that shape and maintain the life on the planet. For these reasons, the longitudinal connectivity has been recognized as the most important and underlying feature of running water environments. Unfortunately, the connectivity is heavily impacted by millions of barriers that have been created by humans in past centuries. Amber Barrier Atlas, that collected so far information on 400,000 barriers, documents the severity of this impact. Our projections allow to expect that about every kilometer of a river we could expect a barrier on European rivers. These barriers are not the same. They are dams, weirs, sluices, culverts, and all of them are having different sort of impact. This impact varies also depending on the communities that occupy the rivers where the barriers are placed on. To address this issue, the scientists of Project Amber analyzed fisheries data collected by European Union and developed classification of rivers into macrohabitat types that can be seen on this map. These macrohabitat types, water bodies that belong to macrohabitat types, are expected to allow for life of specific fish communities that create fish community structure. Fish communities, which are supported by different macrohabitat types, are presented in this slide. They are presented as the community structures, demonstrating proportions of species groups using specific habitat types in the community. Among those habitat use guilds, we can find rheophilic species, which prefer fast-flowing water, and limnophilic species, which prefer slow water and ponded environment. Generalist species are species which are very flexible and adapted to any kind of environment. Obviously, in highland and mountain alpine rivers, we would expect the highest proportion of rheophilic species, and in the lone-run rivers, lower numbers, higher proportion of limnophilic species. Still, as we can observe it here, almost all macrohabitat types are dominated by rheophilic fish, therefore river fish. Consequently, we can expect that building a dam, which tends to create pond environment, would affect the distribution of this fauna. The most well-known impact of barriers on aquatic life is blockage to fish migration upstream. We are very well aware of passage limitation for long-distance migratory species such as salmon, but there is also a plethora of other organisms that migrate upstream in order to fulfill their life cycle. This is, for example, the bream that we can see here on this movie. Another type of impact that is very well known is mortality caused by dewatering or by passage through the turbines. But impacts of barriers are much more complex. Here, at this example, we see comparison of free-flowing river and river with the dam. The major differences are that where we have free-flowing river, we have different substrates, we have species migrating up and down, their distribution of depth and velocity is relatively variable. Whenever we put a dam, there is coming not only connectivity interruption, but also ponding of the river, sedimentation, flow is being altered, habitat is being changed and lost. And downstream, there is also impact mostly connected with change in water flow and the temperature flow, as well as in sediment degradation. So what are the impacts of barriers on upstream habitat? Whenever we put the dam, we can expect increase of the depth, lowering of velocities, increased substrate siltation and accumulation, higher temperatures in summer, and lower oxygen, and frequently eutrophication, which may lead to release of a lot of methane into the atmosphere. Biological consequences is shift in vegetation, as well as distribution of benthic fauna. Considering fish fauna, when we change riverine habitat, as we've seen here on this picture, that is dominated, like in the mountain river, by rheophilic fish gills, and we turn it into a pond, we can expect of change of lotic into lenthic habitats, and therefore very different community structure that is dominated by macrohabitat generalists. With regard to the downstream area, majority of modification is caused by modification of flow regime. This leads to fluctuations of depth, velocity, and the temperature, which might be either higher or lower depending on the specific situation. Furthermore, since sediment is blocked and the river downstream starves for substrate, it leads to riverbed erosion. Obviously, fish migration is blocked and fish mortality is caused frequently by dewatering. Here we see an example of change in water levels and strong fluctuations that are caused by hydropeaking, leading to such mortality. With regard to fish community structure, in unimpounded river, like in this lowland undisturbed river, we will still expect majority of rheophilic fishes, but mostly dominated by rheophilic water column species. After changing of habitat quality and stability and rapid bottom erosion, we observed alter fish community. In order to determine the impact of dams and to find a way of mitigating them, we needed tools that will allow us to define habitat changes up and downstream, to develop mitigation scenarios, and compare those scenarios and select those that are most effective. So what are the parameters that describe these habitat changes? As we've documented before, in majority of cases, the change of habitat is causing the change in community structure. It means it is change of habitat structure that leads to this modification. Secondly, we observe the reduction of suitable habitat area. Some areas become unuseful for dominating species of the community. And thirdly, we observe the limitation caused by temporary habitat deficit, so-called bottlenecks. Habitat suitability models are the most appropriate tool for this purpose. These are tools that create a computer model of riverbed structure and a mathematical model describing the ways in which fish or other animals use their habitats, so-called preferences. The preferences are applied to validate the riverbed structure and hydraulics in terms of habitat suitability. Eventually, the models quantify the amount of suitable habitat as suitable areas. In combination with hydrological time series analysis, all of the before-mentioned parameters can be calculated. The habitat models can calculate these metrics for a variety of pre-selected scenarios, and metrics can be plotted on restoration alternatives analysis diagrams, which represents the effect in Euclidean space, allowing to select the best available scenario. The axes of this diagram are coming from habitat models. The y-axis describes the habitat structure with the similarity index. The habitat stress state alteration describes change between scenarios in temporary habitat deficit. The size of the bubble describes the amount of habitat that is missing and not being suitable at particular scenario. Okay, so let's go now more into a detail how to calculate the three components of the diagram. It means alteration of habitat structure, alteration of habitat stress states, and unsuitable habitat area. The first step should be a choice of habitat simulation model. Our recommended model of choice is Meso-Hapsim model, which has been developed in the last century and tested all over the world. It has been created with the purpose of allowing for analysis at the landscape level, therefore quite adequate for investigating the impact of one or multiple dams. Meso-Hapsim simulation model determines the distribution of geomorphic features such as riffle, pools, and runs under different flow circumstances, together with the attributes that are relevant for fish, such as cover, and allowing them to choose the best available habitats. The habitat suitability is determined also at the similar scale of geomorphic unit, allowing for determination of community structure within every hydromorphologic units, and therefore the model is very adequate to perform analysis for entire aquatic communities rather than only for individual species. Data necessary to create habitat map is collected in Meso-Hapsim with help of drone technology. We then map so-called hydromorphologic units such as riffles and runs, as well as collection of hydraulic data such as distribution of depth, velocity, and substrate in every one of those hydromorphologic units. Suitability of these habitats is defined with help of habitat suitability criteria obtained on the base of literature analysis. These criteria define the ranges of depth, velocity, substrate, and type of hydromorphologic units and cover, which are necessary in order to expect occurrence of specific fish guild. Suitability criteria are developed for guilds, not for individual species. These habitat suitability criteria are applied to develop habitat suitability maps. Depending on how many criteria are fulfilled in one HMU, it is declared unsuitable, suitable, or optimal habitat. The criteria are then applied to entire maps describing the distribution of hydromorphologic units, and in this way we are obtaining maps of distribution of suitable habitat and suitable area. The area of suitable habitat, so the area in green or yellow color, may change with flow conditions as visible here. The amount of suitable area for each species at any given flow that has been measured is plotted in this diagram and then used to develop habitat rating curves. The rating curves present how much of the channel area is suitable for any given gild at specific flow conditions. The area under the curves occurring at the median flow, so flow that happens most of the time, is then used to create habitat structure plot as the one to the right, representing the proportions of channel area that is suitable habitat for each gild. This habitat structure can be compared with community structure, for example, or with habitat structure different scenario, and we developed dissimilarity indices that tell us how much those two structures differ from each other. And this is already a first metric for our restoration alternative analysis diagram, the one that goes on the y-axis. The second metric to be used at restoration alternative analysis diagram is the amount of unsuitable area, which is calculated as a difference between the rating curve representing total amount of wetted area and the rating curve representing a total amount of habitat for so-called generic fish. Generic fish habitat is the habitat area that is suitable for at least one of the species in the community. So if it is suitable for 1, 2, or 3, it is calculated once. And as mentioned before, it can be measured between wetted area and generic fish habitat area. The size of the bubble on the RAA diagram is reflecting proportionally the amount of unsuitable area. To obtain the third metric requires performing habitat time series analysis. To analyze habitat time series, first use community rating curves and combine it with hydrographs, which represent the amount of flow that has occurred in the river at any given day in the long-term time series. The combination of these two diagrams provide us with habitograph, which shows us how much habitat has been in the river at any given day. In order to identify habitat deficits, we analyze the duration of the events when the habitat was under specific habitat levels, and we investigate the events and duration of the events when the habitat was lower than any given threshold. Such analysis is being performed for number of thresholds, observing that the thresholds are very low will be always exceeded, and the thresholds that are very high will be never or very seldom exceeded. Data obtained in this way will be then plotted on the cumulative duration diagram from longest to shortest. This means that the event of 15 days, like in this particular example, will be plotted as a first, and it makes about 20% of the total duration of the summer. The event of 14 days is plotted on top of it, and both of them make about 38% of the time. The second point means that the habitat was under this specific threshold for a duration of 14 days or longer for about 38% of the entire summer. Now, few things need to be observed. The steeper the curve, the less change in frequency between durations. For example, the duration of 13 days did not occur, therefore the curve drops vertically. And in contrast, the more events of the same duration, the flatter will be the curve because they will be added to each other. One more important point to observe, that as we observe the curve from the bottom, all of a sudden we will see the steep change of an angle, and this lowest critical point is considered being a transition to persistent durations. Former diagram represented uniform continuous on the threshold curve for one season and one threshold. When multiple curves, each representing different thresholds, are plotted on one diagram, a pattern can be observed. In the lower left corner of the diagram. Here, the curves for low habitat thresholds are located. The spacing between the curves is at first very small and increases rapidly as we move to the right. This is considered to be transition value from rare events, and the highest of densely packed curve is called rare habitat threshold. Similar pattern can be observed on the other side of the diagram for very high thresholds, the lowest of which is selected as a transition to common events. The critical points of both curves indicate transition to persistent events. One more value is plotted on each of the two curves. It is a duration that did not occur more often than every 10 years. It is considered a transition to events of catastrophic duration. As indicated on the diagram, we can then classify it into events into rare, typical, and persistent. The rare events are indicated by the brown field, are densely distributed curves in the lower left corner, below red line. These are also the events of catastrophic duration. It means those that happened no more often than every 10 years. The typical events are on one hand bordered by densely distributed curves on the right and are shorter than persistent duration. The persistent events are those indicated by light green field that occur above the lowest critical point or rare and typical curve and are shorter than catastrophic. UCAT diagrams can be used to calculate the habitat stress days and the alteration between different scenarios. To explain the concept of habitat stress days, we demonstrate the same habitat duration fields, typical, persistent, and rare, in a different form of diagram, which is called actogram. The actogram demonstrates the duration days on y-axis and percent of channel area that is suitable habitat. On the actogram, the conditions occurring at any given day can be plotted for reference and present habitat conditions, for example. From the moment when the habitat deficit duration exceeds persistent threshold, we speak about habitat stress days. The difference between the habitat stress days at different scenarios is considered to be alteration of habitat stress days and can be used as a metric for measuring of the impact. Alteration of habitat stress days can be measured on UCAT diagram for rare thresholds. We plot the rare thresholds for both scenarios. The distance between the critical points on the curves indicates the frequency change of persistent events. It is expressed as a ratio of habitat stress days from reference scenario. In this diagram, the frequency increase is to 2000% of original, hence the habitat area will be under this threshold for persistent amount of time, about 20 times more frequent. This may be considered deleterious to investigated fauna and could cause the shift in community structure by promoting more flexible and resilient species. This value is plotted on the x-axis of RAA diagram. In this way, we computed all three metrics necessary to develop a restoration alternative analysis diagram. What is important for the interpretation of this diagram is the closer we are plotting our scenario to the origin, the less will be the impact. On this diagram here, we plot hypothetical current conditions, named as CC, future conditions, historical conditions, desired future conditions, and best available conditions. And this allows us to select the best possible scenario. Now we will demonstrate the application of the above concept using habitat data collected on the Mienia River in central Poland. This is a small lowland stream, a tributary of Świda River, which flows into Vistula River. In its lower section, Mienia River flows through a conservation area, but further upstream it underwent some modification with purpose of agricultural irrigation. It has therefore a number of small barriers which are no longer in use. The largest dam in the mid-course supplies water for fish farm. Here you see the location of the impoundment. The downstream section is relatively pristine, and the channel between the fish ponds is inundated. The key attributes of this situation you can see on the slides, and here is the close-up on the dam taken from the drone. This slide is presenting a big picture on the situation with when we look upstream, the fish ponds to both sides of an impoundment, and the close-up where you see the impoundment under very low flow conditions when the sandbars are being exposed. This is a relatively rare situation. The fish community of River Mienia represents macrohabitat type Central European lowland with medium sediment, and this what would be expected in undisturbed conditions. The community is dominated by rheophilic water columned fish, which chub and dace belongs to it, and also rheophilic benthic fish such as gudgeon. The proportions you see in a pie chart to the right. This slide represents the habitat suitability criteria for most dominant species. This is rheophilic water column, highly rheophilic intolerant, and rheophilic benthic. The depth ranges, velocity ranges, substrate type according to the Austrian norm, HMU type, and the cover. About 500-meter long portion of the river downstream of the dam has been mapped multiple times and used to develop a habitat model for the species in the community. This model was then used to simulate 3 scenarios, of which first considered of river without the dam, where impoundment has been replaced with a sequence of habitats similar to those downstream, and the ponds were replaced with the forest. In this scenario, we had two sub-scenarios, sub-scenario A and sub-scenario B. In sub-scenario A, we used the historical flow records from 1974 to 2000 for habitat time series analysis. You see to the right the duration curve for this flow records. Second scenario, sub-scenario was simulated near future flow conditions, where we incorporate also impact of climate change. The near future considered the years 24 to 50. The climate change impact has been modeled with 9 climate change models, and median of flows predicted with 9 models was used for time series analysis. In scenario 2, the dam was in place, so practically current conditions. And again, sub-scenario A with historical flows, and sub-scenario B with simulated near-future flows. They're also shown on the duration diagram. Obviously, the flows are predicted as being a little higher after impact of climate change. Since this third scenario was supposed to investigate use of the impoundment for flow augmentation in the river during the summertime low flows, we had to first develop habitat time series analysis and use U-cut curves analysis in order to define the amount of water at which the augmentation needs to be put in place, as well as persistent durations that would trigger the augmentation. We developed the U-cut curves for scenario 1A and plotted U-cut curves diagram. As a rare threshold, we chose 32% of channel area of suitable habitat and with 19 days of persistent duration. In this scenario, amount of flow providing 32% of habitat would be equivalent to 180 liters per second. To provide the same amount of habitat with the dam in place, 250 liters per second would be necessary. Consequently, the scenario 3 represents river with the dam and flows augmented from the ponds according to the following scheme. When the flows in the river are less than 250 liters per second for 18 days, which is smaller than rare persistent threshold, the flows were increased to 400 liters per second. Again, we have sub-scenario A with historical flows, and the duration curve diagram represents how little of a change this would cause to the historical condition. Scenario 3B, again, simulated near future flows, and duration curve that represents how small of a difference it will cause in the future flows as simulated. So here are the first results of investigating impact of dam on Mania River, and the first we compare scenarios A and B in terms of habitat structure dissimilarity. The proportion of the available habitat for fish gills at these two scenarios differ by only 10%. However, impoundment created by the dam reduces habitat for rheophilic water column sand gravel species and the limnophilic, phytophilic, moderate tolerant species. Because it is a lowland river, doesn't seem to be a lot of change. In terms of unsuitable habitat, in both scenarios, there is practically no difference between wetted area and generic fish habitat. It means entire wetted area is used by the fish. After performing habitat time series analysis, we can investigate the change in habitat stress days. And in scenario 1, we comparing historical flows with simulated near future flows, because that's the only difference that we can have between scenarios. And here, the number of habitat stress days in the near future conditions actually lower than under historical conditions, so the alteration of habitat stress days can be considered zero. Because the river is not absolutely pristine and probably has some impact, this can be seen as improvement of current conditions. With regard to scenario 2, the river with the dam, the conclusion is that under historical flows, putting the dam in place increases number of habitat stress days compared to the situation without the dam by almost 40 times. Whether under simulated near future flows, this number is a little smaller, but it's still 30 times increase in the number of stress days. Both of the impacts can be considered severe compared to other studies that we have done before. Introducing flow augmentation under historical flow conditions would reduce the alteration of habitat stress days from 40 to 20 times, and under simulated near future conditions actually from 30 to 23 times. When we plot all these scenarios on the restoration alternative analysis diagram, it becomes apparent that compared to today's situation, the first of all flow augmentation will reduce the impact by not a lot. Climate change would also reduce the impact in terms of number of stress days. However, the dam removal would drastically reduce the impact of this dam. Obviously, these are just few scenarios used as an example to demonstrate the utility of the RAA diagram. Developing some other scenarios would probably allow to find most optimal solution for this situation. In conclusion, we can state that restoration alternative analysis allows to identify impact of dams on fish habitats. Mitigation alternatives such as flow augmentation strategies can be tested. Best available scenarios can be easily identified. And surprisingly, even on small lowland river, the impact of dam is substantial. This, I would like to present you some references and the members of our Amber consortium. Thank you.